Hi there, my name is Kellen Billadu, and today I'll be going over Lab 3. So the purpose is to quantify the relationship between the distance the magnet is away and the B field it produces at that location, and then compare the physical and computational examples that we've done. So the model is you're just taking a phone with a magnetometer app, I used Firefox, and putting it certain distances away and measuring the B field at those locations. All right, so the system is the magnetometer, the surroundings, or the bar magnet in the Earth. We're assuming that there aren't any other magnetic influences, and if there are, they're insignificant. And initial conditions, right? B net is 0 when R is infinity, and then we're going to move the phone closer to certain distances and measure the B field at those locations. Cool. So some of the physical principles, we're given three equations. One of them is for a bar magnet, which is just dependent on constants K and N. The on-axis B field is mu naught over 4 pi times 2 mu over r cubed, where mu is the moment. And then we are also provided another equation, which is used in the code. It's just the magnetic field created by a dipole at a certain observation location. So here's the result preview. On the left is what I got from physical experiments and inputting the distances in B fields. There was the on-axis and off-axis. And then we produced a natural log K and N from that. And then on the right is the code and the results produced by that. So for the experiment, the first part was just to move it along the ruler and put in some distance and B field values to produce the graph on the right, as well as the natural log K and N values. And then you can use those values to calculate mu, right? So using those two equations that we saw earlier, the on-axis equation as well as the bar magnet equation, you can produce a U of 1.545 newton meters per Tesla. And then the second part of the physical experiment was just putting it a certain distance away until you hit a certain B field value, and then going up that same distance and finding B field at the 45-degree angle, where you can see the B net in the bottom right-hand corner there. So now for the code. So the first part of the code was to produce a dipole using the radius as well as certain constants, and then certain hat vectors. And then we made a bunch of observation arrows, two of them on axis, four of them off axis, as well as um, one at the 45, which is that bottom section down there. And that's supposed to kind of mirror what we did in the physical model. And then you can see some of the results there on the left. Now, so for similarities and differences, the experimental and simulated values are very, very different. You can see the results next to the B net. There is no Z component for the simulation, so that's one big difference. And then the simulation Y component is much, much larger, resulting in like a order of difference for the B net. So some sources of error are other magnetic sources that I didn't take into account. Some faulty gathering of data, right? Like if I rotated it in some way so that the Earth would change the B field in some way. And then also the app was changing that value a ton. Like maybe I looked at it at the wrong time and measured it wrong, or just the app was just acting up because it did that sometimes. Now, if you change the angle of the phone, the Earth affects it produces a different B field depending on the rotation of the phone. It doesn't produce a different Z value, it stays mostly the same, but the X and Y values will change. So you have to compensate for that in the calculation. Now, if you stick two magnets next to each other, which I did, I actually tested that, they still act like a dipole. The magnetic field is just about double if you put them end to end, and the dipole moment will also change. All right, that's it. Thanks.